Welcome back to another mathematics session. It's so nice to see all of you here, ready for class. And this goes to show that you have been enjoying the whole topic of matrices and you're looking forward for more. Well, I am here and we're going to be looking at some other aspect of matrices, and no doubt we're going to try as much as possible to enjoy the class just as we have done before. All right. Now, if you notice here that right behind me, the things that we will be looking at for this session is that we're going to continue a little bit more on singular matrices. Good. We want to see how we can use the concept of singular matrices to solve problems. All right. Now, the next thing that we want to do is to be able to find the adjoint matrix for a 2 by 2 matrix. All right. We want to be able to find the adjoint for a 2 by 2 matrix. And last but not least, today we will be looking at the inverse of a 2 by 2 matrix. We're going to be looking at the inverse of a 2 by 2 matrix. Now, let's go. Now, in our last session, we looked at singular matrices. What are singular matrices? Yes, a singular matrix is a matrix whose determinant is equal to 0. So, for example, if you should go to the exam, or if you're working and you're practicing, you should see a question that says, determine if this matrix is a singular matrix. What is it that you will do to determine that? You will have to find the determinant. Now, for a singular matrix, the determinant can only be equal to 0. Or the question could ask, show that the matrix A is a non-singular matrix. Show that the matrix A is a non-singular matrix. Now, if it is a non-singular matrix, it simply means that the determinant can be any value except for 0. So all you need to do to show that it is a non-singular matrix, just work out the determinant. All right, let's look at some questions and see how we go about doing those. All right, so for example, just by way of recap, if I should put the matrix A and I say we have -5, we have 2, we have 10, we have -1. And I want to determine if that matrix is a singular matrix. All right, so determining if A is a singular matrix, all I need to do is to find the determinant. Now, the determinant of A, as was mentioned in the last session, the notation, this is how we write the determinant of A, and that is going to be equal to the product of the leading elements, which is the one in your top left and your lower right. So the product of the leading, which would have been -5 times 2, minus the product of the non-leading, which would have been 10 times -1. Now let's multiply and see what happens now. -5 times 2, that will give us -10, minus 10 times -1 will give us -10. All right, now notice here, it is the negative of a negative. And we know that when two signs comes beside each other like this, we need to rewrite them as 1. If the signs are the same, then it becomes a positive. So here we can now write it as -10 plus 10. We owe 10, we have 10. So when we pay what we owe with what we have, then we don't owe anything and we don't have anything. So therefore, our answer is 0. Yes, the matrix A is a singular matrix because the determinant is equal to 0. Now, a lot of students tend to have this thing about them when you ask what makes a matrix singular. They say because it is equal to 0. I don't want my student to speak like that. I want you to tell me exactly what is happening. What makes it a singular matrix? It is a singular matrix because the determinant is equal to 0. Not because it is equal to 0. It is the determinant that should be equal to 0 for it to be a singular matrix. Okay, so A is a singular matrix. Now let's look at another problem and see how we would go about working this out. Now, if I give you the matrix B, and I tell you that the matrix B, this is X, this is 2, this is 6, and that is 4. And I say to you, given that B is a singular matrix, determine the value of X. Given that the matrix B is a singular matrix, they want you to tell them what the value of X is. No, I know for sure, for this one, it is very, very simple because a lot of us can just look at it and know what the value of X is. However, let us see how we should approach this. Now, the moment you see the word singular, we know that for it to be singular, then the determinant must be equal to 0. So let us set up our equation here. So the determinant of B is equal to, it is going to be the product of the leading. So it is going to be X times 4 minus 6 times 2. Here I'm going to get 4x minus 12. Now, the determinant of the matrix must be equal to 0 in order for it to be a singular matrix. This is how we find the determinant. Product of the leading minus the product of the non-leading. But for it to be a singular matrix, this thing here must work out to give you 0. Now notice here now that we end up with a simple equation. A simple equation that we need to solve. Now here we have 4x minus 12. We need to solve for x. We could just look at it and know what it is. Because for me to take away 12 from a number, that will end up giving us 0. Then that number here must be 12. And I could say, what should I multiply 4 by to give me 12? Then you realize that it is going to be 3. Right? For those persons who will not be able to pick it up so quickly, then we just go ahead and solve. We can use the balancing method. So to get rid of the 12, we're going to have to add 12 to both sides. So it becomes 0 plus 12 equal to 4x minus 12 plus 12. That cancels out. 0 plus 12 will give us 12. And that is now equal to 4x. Now, what operation connect the 4 to the x? Yes, it is multiplication. Now, to remove the 4 from off x, we have to now do the inverse operation, which is to divide. What we do on one side, we have to do it on the other side. So we divide that side by 4, we divide that side by 4. Now, x is now isolated. X is now by itself. So x is now going to be equal to 3. So the value of x here is 3. That is the value that will make the matrix B a singular matrix. That would be the value that makes matrix B a singular matrix. Good. Let's try one more, and then that's it as it relates to the singular matrices. We will now move on to the adjoint, which again is very, very simple. So let's go. No, the matrix R 2A 5 3 4. That's the matrix R. Now, the question could be structured in such a way that given that the matrix R is a singular matrix, determine the value of A. Or they could say, determine the value of A for which the matrix R is a singular matrix. Same procedure. All we need to do here is to say, okay, determinant is equal to 2A multiplied by 4 minus 3 multiplied by 5. That's how we go about finding the determinant. 2A times 4 will give us 8A minus 3 times 5 will give us 15. Good. So now we have our determinant there. 8A minus 15. But for the matrix R to be a singular matrix, then the determinant must be equal to 0. So therefore, it should be equal to 0. Again, we have a simple equation that we need to solve. So we're going to have to add 15 on both sides because they're subtracting it here. So that's 0 plus 15 equal to 8A minus 15 plus 15. That will go out. We're left with 15 equals to 8A. Very, very simple. Now it's time now for us to get rid of that A, not the A, the 8, so that we can isolate the A. So 8 is connected to A by a multiplication. So to get rid of it, we have to divide. What we do on one side, we do it on the other to keep it balanced. So this is going to be A equals to 15A. All right. So in this case, the value of A is going to be a fraction. Now, why is it that I really choose a question like this? The reason for that is that a lot of times students want to just look at it and say, okay, the value is that value. They're not always going to be that easy. So therefore, you need to understand the whole concept of working it out. And that's how we end up with 15 over 8, 15A. All right. So there we have it. We have looked at how we can solve some problems as it relates to the singular matrices. So now it's time for us to move to the adjoint of the 2 by 2 matrix. All right. So let's now look at how we go about finding the adjoint of a 2 by 2 matrix. Now, in order for us to find the adjoint of a 2 by 2 matrix, we have two simple steps that we need to follow. Two very, very simple steps. All right. Now, let's start out with the matrix M, and M is equal to A, B, C, and D. Now, in order for us to find the adjoint matrix here, all we need to do is to interchange the leading elements. All we need to do is to interchange the leading elements. That's step one. Step two, multiply the non-leading elements by -1. Multiply the non-leading elements by -1. So that's all we need to do. So the adjoint of M what is it that we're going to do to find the adjoint? We're going to interchange the leading and then multiply the non-leading by -1. So that would have been D, -B, -C, and A. That's all we need to do to find the adjoint. And it's very, very important that you know, because if you notice, we're moving on to find the inverse of the 2 by 2 matrix. And if you don't know how to find the adjoint, then you will have a problem when you're working with the inverse. So that's all we need to do. Interchange the leading elements and multiply the non-leading elements by -1. So let's look at a few questions and see how we go about doing that. The matrix S is equal to 3, -5, 2, and 1. If I want to find the adjoint, then the adjoint of that matrix, we're going to interchange the leading elements and multiply the non-leading elements by -1. But by this, you should realize that to multiply by -1, all you're doing there is changing the sign. Good? So this is what you're going to have to do. The adjoint here is going to be 1. -1 times -5 will give us +5. -1 times 2 will give us -2. And then we have our 3 here. So we interchange the leading. We interchange the leading and then multiply the non-leading by -1, which is just changing the sign. Let's try another. A is equal to -4, 6, -7, and 5. Now, please remember, students, that to find the adjoint for this matrix, all we're doing here is interchanging those two. So we're interchanging the leading elements there. And I must multiply this element by -1 and this element by -1. That's what we're doing to find the adjoint. So if I interchange the -4 and the 5, notice we end up with 5 here. When I multiply -1 by +6, we're going to end up with -6. -7 times -1 will give us +7. And then the -4 comes down here. So there you have it. That's now our adjoint matrix for A. Very, very simple, and I know that you're enjoying it. Let's move on to the inverse of a 2 by 2 matrix. Let's move now to the inverse of a 2 by 2 matrix. Now, when we talk about the inverse of a 2 by 2 matrix, what we're actually referring to is the multiplicative inverse. The multiplicative inverse. Now, in lower school, you would have learned about the additive inverse and the multiplicative inverse. For the multiplicative inverse, we know that you're multiplying a number by its inverse and it results in 1. For the additive inverse, you're adding a number to the additive inverse, you must end up with 0. In this case, we're looking at the multiplicative inverse. All right, so let's see, and I will tell you the connection there with what we learned before and the whole matrix that we're talking about now. Now, if I should give you the matrix A, I will start off with A, B, C, and D. And I ask you to find the inverse of A. Now, to find the inverse of A, then the inverse notation would have been written like this. This is A to the negative 1. That is the notification of the inverse. So it's the inverse notification. All right. Now, how do I find the inverse of the matrix? It is going to be 1 over DET multiplied by the adjoint. So now you realize now that the inverse is not difficult because everything that you need to know as it relates to finding the inverse of a 2 by 2 matrix, you already know it. 1, DET stands for the determinant. You know how to find the determinant. 2, you already know how to find the adjoint. And then now you realize that the inverted determinant becomes a scalar quantity for the adjoint. We already would have discussed scalar multiplication. So this is now very, very simple. So let's go. If I want to find the inverse of this matrix, then it is going to be 1 over the determinant. How do we find the determinant? Product of the leading. So it's going to be A times D minus the product of the non-leading, which is C times B. Let us now find the adjoint matrix. Now for your adjoint matrix, remember what we did to find the adjoint is to interchange the leading elements. We interchange the leading elements. So we interchange A and D. So D go up there and A come down there. Then the other 2 elements, all we need to do is to multiply them by negative 1. So this now becomes negative B and negative C. So here we have it, 1 over AD minus BC times the adjoint, which is D, negative B, negative C, and A. Now, here we have now our scalar quantity. And remember, when there's a scalar quantity, what we need to do is to use that scalar quantity to multiply each term inside the bracket. So our final answer would have been D over AD minus BC, negative B over AD minus BC, negative C over AD minus BC, and A over AD minus BC. So that would now be our final answer as it relates to our inverse. Good? Now, let us see if we can now apply this concept to find the inverse of a few matrices. Ready? I'll give you a couple seconds to just write that off. All right, I remember we're living in the technology world, so sometimes to just speed up the process, what you can do is just send up a pick, and then later on, you can just write the information off in your book. So that's a much faster way to get your information. All right, so let's go. Now, if I should give you the matrix R, and R is equal to say 2, 3, 1, and 4, and I ask you to find the inverse of R, then it is going to be R inverse equal to 1 over DET, which stands for the determinant, times the adjoint. All right, so let's go. So it's going to be 1 over 2 times 4 minus 1 times 3, or adjoint. What would be our adjoint now? Very good. We interchange, so it's going to be 4 and 2. Multiply the non-leading by -1, so it's going to be -3 and -1. Now, when I work this out, I'm going to get 1 over 2 times 4 is going to give us 8. So that's 8 minus 3, 4, -3, -1, and 2. This will now give us 1/5 of 4, -3, -1, and 2. Good. So at this stage, we're going to now use our scalar quantity to multiply each element inside. Now, multiplying by 1/5 is the same thing as dividing by 5. So all I need to do here is to have 4/5, -3/5, -1/5, and 2/5. There we have it. And that now would be our inverse of the matrix. Very, very simple. So we're going to now look at the last question as it relates to this session. And then I'm going to explain to you what I was saying about the multiplicative identity. All right. The multiplicative inverse, sorry. The multiplicative inverse. All right, so let me get rid of this. So if I should give you A, and A is equal to 2, 3, 1, and 2, and 1, I ask you to find A inverse, and 2, I would ask you to find A inverse multiplied by A. A inverse multiplied by A. So this is the last question for this session. So let's go. Now, I could clean this part here just to get a little bit more space. Now, the inverse of A inverse is equal to 1 over the determinant multiplied by the adjoint. And I would love for you, students, that every time you're asked to find the inverse of a matrix, you could just practice to write out this formula. It will help you. So let's go. 1 over 2 times 2 minus 1 times 3 over adjoint is to interchange the leading. But if you notice, the leading elements are the same, so we really don't need to do anything there. So it's going to be 2 and 2, -3, -1. So now we end up with 1, 4 minus 3 times 2, -3, -1, and 2. Now 4 minus 3 is going to give us 1. 4 minus 3 is going to give us 1. So we'll end up with 1 over 1 there. But 1 over 1 is the same thing as 1. It won't change anything. So we don't need to really write it here. So my inverse would have just been the adjoint. So it's now 2, negative 3, negative 1, and 2. So that now would be our inverse. Now, let us just come to the side right here. Just for a minute. If I should have 2, the number 2, and I decide to multiply the number 2 by the multiplicative inverse. Now, the multiplicative inverse of 2 would have been a half. So you reciprocate it. So that's the multiplicative inverse. If I multiply 2 by its multiplicative inverse, then that will end up giving you an answer of 1. So you will get 1 for it. Good? Keep this in mind, and then we're going to work the next part of the question, and then I will explain something as it relates to the answer that we get there. Now, A inverse times A. Now, A inverse times A, it falls under your general multiplication. A inverse times A falls under the general multiplication. So what we're going to do, here we have A inverse here. So A inverse A is equal to 2, negative 3, negative 1, and 2 times A, which is here, which is 2, 3, 1, and 2. Good? So now we have the general multiplication to carry out there. So how do we go about doing that? We use our distributive property. So those 2 in the first will be distributed to that 2, while these 2 will be distributed to that 1. Now, please note that we have 2 columns there, so the distributive thing that we're using must be done 2 times. So ready. So we open our bracket here. We're going to slide down the 2 and the negative 1. What do we map it onto? We map that onto 2. So both of them must be multiplied by 2. Plus, we slide down the negative 3 and 2. Now what do we map that onto? We map that onto 1. So both of them must be multiplied by 1. Now we're through with that first column. So we need now to go over to the second column. So we do our mapping there. So let's go. Sliding down 2 and negative 1. And we map it now to 3. Plus, we're sliding down negative 3 and 2. And we're mapping it on to 2. Good? So we have it there. Running out of space, so let me just rewrite this. Just rewrite it so that you can see what is happening there. So this is going to be equal to 2, negative 1 upon to 2 plus negative 3 and 2 upon to 1. Then we end up with 2 and negative 1 upon to 3 plus negative 3 and 2 upon to 2. All right, very good. Now, let's now multiply. 2 times 2 will end up with 4 plus negative 3, which is the same thing as minus 3. 2 times 3 will end up with 6. Negative 3 times 2 give us negative 6. Negative 1 times 2 give us negative 2 plus 2. -1 times 3 give us -3 plus 4. Now, if I should work this out now, students, notice 4 minus 3 is going to give us 1. 6 minus 6 is going to give us 0. -2 plus 2 is going to give us 0. -3 plus 4 is going to give us 1. Now, I would love for you, any of you, to tell me the name of this matrix here. Very good. So this matrix, we refer to it as your identity matrix or the unit matrix. Now, what's the connection with what I here? Notice when I multiply 2 by a half, which is the multiplicative inverse, we end up getting 1. Now, when I multiply the matrix A by its inverse, we end up getting the unit matrix. The unit matrix, it operates like 1. So if I use the unit matrix to multiply another matrix, it will not change its identity. You will end up with that matrix just the same. Now, this is where we will have to stop for today's session, but I look forward to see you again when we will actually use the inverse of the 2 by 2 matrix to actually solve simultaneous equation. So until we see each other again, I beg of you to keep on practicing. The exam is right around the corner. It's not beyond any of you. It doesn't matter what situation you're in. The important thing is that when you would have gotten the knowledge as it relates to the different subjects, if you keep on practicing, I am 100% certain that you're going to do well in your exam. So until we see each other again, have a good day.